Advanced communication, advanced electronics, VLSI fabrication. For the fabrication of semiconductor devices, the substrate must be in single crystal form. Silicon, the most commonly used semiconductor, is abundantly available on the Earth's surface in the form of sand, which is almost pure silica SiO2 after chemical purification reduction of silica, very pure 99.999% polycrystalline silicon is obtained, which is used as starting material for single crystal growth. Single crystal silicon for integrated circuits is most grown by two methods, namely the Yugoslavic and the float zone techniques. Doping and impurities. In order to fabricate semiconductor devices, a controlled amount of impurities has to be introduced, doped selectively into a single crystal wafers. There are three basic methods used for controlled doping of a semiconductor, namely epitaxy, diffusion, and non-ion implantation. Epitaxy, the term epitaxy literally means arranged upon. In this process, a thin layer of a single crystal semiconductor, typically a few nanometers to a few microns, is grown on an already existing crystalline substrate such that the film has the same lattice structure as the substrate. Epitaxy can be further classified into vapor phase epitaxy, VPE, liquid phase epitaxy, LPE, and molecular beam epitaxy, MBE. The basic principle underlying this process is that the dopant atoms migrate from a region of high concentration to a region of low concentration. The diffusion profile is given by capital N of x comma t equal to n naught into ERFC whole bracket x numerator part denominator part 2 root dt. Dt is under root, close everything close, plus nb, n naught ERFC of x by 2 root dt plus nb, where nb means original doping concentration of the sample, n naught means solid solubility of the dopant in the semiconductor at the process temperature, d means diffusion coefficient of the dopant in the semiconductor at the process temperature, t means diffusion time, x means distance from the sample surface. Theoretically, group 3 elements such as aluminum or gallium, which have sufficiently low ionization energies, can be used as p-type dopants in silicon. However, the diffusivity of these materials in silica, which is the most commonly used masking materials, is very high. During diffusion, gallium therefore has a tendency to diffuse in the regions protected by silica. As the diffusivity of boron in silica is very small, such problems are not encountered in boron diffusion. Boron is thus exclusively used as the p-type dopant in the silicon technology. Ion implantation. Ion implantation is an alternative technique used for selective doping of semiconductors. The doping profile is more precisely controlled by this technique. Also, it is a low temperature process. Another advantage of ion implantation is that it allows the doping profile to be tailored with a greater degree of flexibility. In an amorphous material, the doping after implantation is given by n of x equal to q naught, numerator part అనేది denominator part delta rp 2 pi under root into అంతా separately into exponential of ఇదంతా minus half into numerator part x minus rp denominator part delta rp then x minus rp by delta rp whole square. Delta rp means standard deviation of the projected range. Q naught means total implantation dose, number of impurity ions introduced per unit area. Q naught equal jt by q, where j equal current density and t equal time. Dielectric films. In semiconductor processing, dielectric films essentially serve three purposes. They can be a part of the active device, for example gate oxide of a MOS transistor, used as mask to protect against diffusion or ion implantation, and used as a protector layer also known as passivation at the end of device fabrication, so as to protect the device from harsh ambience and ensure reliable operation. The most commonly used dielectric material in the semiconductor technology are silica and Si3N4, SiO2 and Si3N4. Thermal oxidation of silicon. Thermal oxidation is the most widely used technique to grow silica on silicon. This is usually carried out in an open tube quartz furnace at a temperature range of 900 to 1200 degrees centigrade in an atmosphere of dry oxygen or water vapor, wet oxygen, oxidation. Oxygen is passing through the tube where it reacts with silicon to form silica by means of the following reaction. Si plus O2 gives rise to SiO2, wet oxidation. High purity deionized water kept in a quartz bubbler at the inlet of the furnace is heated to a temperature close to its boiling point, where water then acts as the oxidizing agent, and the oxidation reaction is given by Si plus 2H2O gives rise to SiO2 plus 2H2. This thickness can be expressed by a linear parabolic relation represented as d square plus ad equal to b into 1 plus t plus 2, known as D-Land-Groove model. Small d square plus ad equal capital B into t plus tau. Small d means oxide thickness, A and B coefficients that depend on oxidation temperature and ambient conditions. T means oxidation time. Tau means a parameter for fitting the initial value of oxide thickness. Masking and photolithography. For the fabrication of semiconductor devices, electrodoping is often necessary. This is done by covering the entire sample by a protective or masking layer and then removing this mask layer at some selected regions by a process called photolithography. The most commonly used mask material in silicon technology is silicon dioxide (SiO2), and it can be easily grown on silicon by thermal oxidation, as discussed in the previous section. For compound semiconductors, silica and Si3 and 4 deposited by chemical vapor deposition can be used as masks. Since ion implementation is a relatively low temperature process, photoresist itself can be used as a mask against implantation. Patterning is a two-step process. A photosensitive material, photoresist, is spin coated on the entire sample surface. In optical photolithography, the photoresist coated wafer is exposed to UV light through an appropriate mask plate or photomask. The second step of patterning, the mask is removed, etched from the regions no longer protected by photoresist. If the masking layer is silica, etching is usually done by dipping the sample in hydrofluoric acid wet chemical etching, which etches silica in the regions which are not protected by the photoresist. Metallization. After the fabrication of the device, ohmic contacts with the different regions of the device have to be provided by metal deposition. Also, in case of integrated circuits, different devices on the chip must be suitably connected. Interconnection to perform the desired circuit operations. Aluminum is most widely used in silicon technology for providing ohmic contacts. VLSI design. VLSI design is a sequential process of generating the physical layout of an IC. Starting from the specification of that circuit, it can be fully or semi-automated using numerous software called electronic design automation or computer aided design tools called as CAD tools. The process of developing a chip from concept to silicon is divided into the following four tasks: design, verification, implementation, and software development. Design often starts with marketing, research, and product definition and is followed by system design. It ends with register transfer level RTL coding. Verification is a means of ensuring that the chip can perform faithfully in functionality according to its design specifications. It includes verification at the system, RTL, and gate levels, and sometimes even at the transistor level. The bug finding struggle continues until the chip is ready for production. Implementation is the process of actually creating the hardware, which results in an entity that one can see and feel. Includes both logical and physical implementations. Software development is the process of programming the brain of the chip, the on-chip processors, that is called as software development. Remember, there are two design styles used in VLSI design. One is the top-down approach, another is the bottom-up approach. The top-down approach, the system is built starting the top up to bottom, while in the bottom approach, the basis building blocks are built first and they are combined or assembled to build the entire system. VLSI circuit design process an interactive process that refines an idea to a manufactured device chip through the least 5 levels of design: abstraction, hierarchical decomposition, or divide and conquer is a useful methodology that partitions the entire system into its components. The components are again partitioned into modules, and this process continues until the basic building blocks are reached. Basically, there are 5 levels of abstraction: functional or architectural, registral transfer level, brackets module or functional block, third one logical design, fourth one circuit design, fifth one physical design. So the design of IC starts with an idea that, and then The whole design is broken into modules and submodules. There are 5 hierarchical levels into which the design can be broken. The designer working at any level is unknown about the work at another level. The IC design can be described in the following 3 domains: behavior, structural, physical. The 3 design domains are represented pictorially by a chart called the white chart as shown in figure below. The design process at various levels is usually evolutionary in nature. It starts with a given set of requirements. Initial design is developed and tested against the requirements. When requirements are not met, the design has to be improved. When an algorithm is designed, then it is implemented using functional blocks. Floor planning is done to decide the size of the design and the location of the functional blocks. Next, architectural abstraction, physical domain, architectural of ICs, PCBs, used packages used to build the system hardware. Structural domain, PC, brackets, total system. Behavioral domain, software code of the entire system. Logical abstraction, the logical abstraction, physical domain, various units in the architecture, memory units, controlling units, etc. Structural domain, types of processor, RISC used to build the system. Behavioral domain, operating systems, programs written to make the system run. Circuit abstraction, in circuit abstraction, physical domain, cells used as standard cells or semi-customs. Structural domain, adders or registers, multiplexers, etc. Behavioral domain, subroutines or functions in the program. Physical abstraction, in the physical domain, transistors in the cells. Structural domain, transistors layouts. In physical abstraction, behavioral domain, instructions based level in the program. Remember, behavior level design is what we think. Structural design is the block by which the thought will be implemented. And physical design is the actual placement of transistors to complete the design. Behavioral design is what we think. Structural design is the block by which the thought will be implemented, and physical design is the actual placement of transistors to be complete the design flow. A design flow is a sequence of operations that transform the IC designer's intention, usually represented in RTL format, into layout, concept and market research. A detailed research about the tools available for designing the IC according to the specifications given in the requirement documents is done thoroughly. Architectural specification and design constraints. The design idea refined into a set of requirements is known as specification. The general specification are what does the chip do, how fast it need to operate in order to compete in market, how much power will it consume, how big will it be, how much time it takes to design the chip, how effectively it can be tested. The flow chart is as follows. Concept plus market research, architectural specifications and RTL coding or HDL capture, RTL simulations, logic synthesis, optimization, formal verification, brackets, RTL versus gates, pre-layout STA, timing or not, floor planning, replacement, global routing, next transfer clock, tree to compiler, formal verification, global mute STA, timing okay, detailed routing, post layout STA, next tape out. HDL capture and RTL coding. Two HDL languages, Verilog and VSDL, have been standardized and have emerged as the tools for IC design. And HDL is created to meet a number of needs in the IC design process. HDL allows the description of the structure of a hardware system. HDL can be used to describe how the system is decomposed into building blocks and how these building blocks are interconnected. It allows the specification of the system functionality by using the form of familiar programming language. The design of a system can be simulated before being manufactured, so that designers can quickly compare alternatives and tests for corrections without the delay and expense of hardware prototyping. It allows the detailed structure of the design to thus synthesize from a more abstract specifications, allowing the designers to concentrate more on strategic design decisions. This automation systems process also helps reduce the design implementation time. Logic simulation. Simulation is the use of a computer program to simulate the operations of a digital circuit. Logic simulation is the primary tool used for verifying the logical correctness of the hardware design. Next, RTL simulation. The logic correctness of the RTL description is checked by simulation by applying test vectors or by running test bench program. Logic synthesis. Logic synthesis is the process of translating in abstract form how desired circuit behaves typically in RTL into a design implementation in terms of logic gates. Remember, while synthesizing the design, logic gates that are used are taken from standard library provided to the designer. Logic optimization. The logic optimization is a part of logic synthesis. You use the process of finding an equivalent representation of the specified logic circuit under one or more specified constraints. The basic constraints are, remember, while synthesizing the design, logic gates that are used or taken from standard library provided to the designer. Logical optimization. Logical optimization, a part of logic synthesis, is the process of finding an equivalent representation of the specified logic circuit under one or more specified constraints based on circuit representation. First one, two-level optimization. Second one, multi-level logic optimization based on circuit characteristics. Sequential logic optimization, combination logic optimization, formal verification. Verification is the process of checking the design's functional correctness. Static timing analysis. Static timing analysis (STA) is a method of computing the expected timing of signals inside a digital circuit without using simulation. Remember, a whole time violation when a signal arrives too early and advances one clock cycle before it should. A setup time violation when signal arrives too late and misses the time when it should advance. Floor planning. The layout tool generates the layout and performs the placement and routing. Floor planning is the first major step in physical design. Placement. Placement is the process of placing the cells or searching for the appropriate location within the chip floor plan for each cell in the netlist. Routing. After the placement step, the exact locations of the cells and their pins are fixed. The next step is to physically complete the interconnections defined in the netlist. Tape out. It is the time at which the design is fully qualified and ready for manufacturing. Layout of the design is sent to the manufacturing lab. Design styles. Depending on the application, cost of production, performance, and the volume of production, there are different VLSI design styles that are followed to implement a chip. Each of the style has their own advantages and disadvantages and is chosen on the basis of the target application. The commonly used design styles are as follows: FPGA, field programmable gate array design, standard cell based design, full custom design, semi-custom design, programmable logic device (PLD). Difference between FPGA and ASIC, application specified integrated circuit. FPGA purchased from vendor as a standard part, then programmed by the user. FPGA, no production setup costs. First unit costs then same as subsequent units. Fixed unit costs. Fast turnaround time can be programmed in a matter of minutes in FPGA. In FPGA, relatively high per unit cost and low capability per chip. In FPGA, design requires mostly writing HTML code in VSDL or Verilog. In ASIC, application specific integrated circuit made to customer specification by the vendor. High production setup costs, often in the $100,000 range. Slow turnaround time, often at least 6 weeks. ASIC, lower per unit cost, good for higher volume production. Design often requires knowledge of the physical layers of silicon inside the IC. Now comparison between FPGA and CPLD. FPGA means field programmable gate array. Performance depends on the routing implemented for a particular application. In FPGA, functionality is implemented by lookup tables. In FPGA, suitable for medium to high density designs. In FPGA, more complex and register rich architecture. In FPGA, channel based interconnection fabric. In FPGA, can be programmed as many times as possible. CPLD, complex programmable logic device. In CPLD, predictable performance independent of internal placements or routing. CPLD functionality is implemented by PAL-like structures, suitable for low to medium density designs. Regular PAL-like architecture, crossbar type interconnection fabric. CPLD can be programmed a limited number of times. Next, area, full custom small, standard cell based small to moderate. Area, gate array moderate. In area, FPGA large. Performance, full custom like high, standard cell based technology high to moderate. In gate array like moderate, FPGA like low. Fabrication layers, full custom like all, standard cell based like all. In fabrication layers in gate array like metal layers. In fabrication layers in FPGA like none. Design time, full customer high, standard cell based is high to moderate. Design time for gate array is moderate. Design time for FPGA is low. Now, cell size, full custom variable. Standard cell based అయితే fixed height, cell size of gate array is fixed, cell size of FPGA is fixed, cell size of PLD is fixed, cell type of full custom is variable, cell type of standard cell based is variable, cell type of gate array is fixed, cell type of FPGA is programmable, cell type of PLD is programmable. Cell placement of full custom is variable, cell placement of standard cell based in row, cell placement of gate array equal fixed, cell placement of FPGA is fixed, cell placement of PLD is fixed. Interconnection full custom is variable, interconnection standard cell based is variable, interconnection gate array is variable, interconnection FPGA is programmable, interconnection of PLD is programmable. Pipelining is to arrange the hardware so that more than one operation can be performed at the same time. The number of operations performed per second is increased even though the elapsed time needed to perform any one operation is not changed. Pipelining is a particularly effective way of organizing concurrent activity in computer systems. There are two types of pipelining: instruction pipelining, arithmetic pipelining. Instruction pipelining consists of multiple sections, each of which perform one of the functions of the instruction cycle. For all instructions, performance analysis of pipeline. Cycle time tau equal to maximum of ti plus d, that equal to t tau m plus d, where tau m means maximum stage delay through stage which experiences the largest delay. K means number of stages in the instruction pipeline. D means time delay of a latch needed to advance signals and data from one stage to the next. In general, the time delay d is equivalent to a clock pulse, and tau m is greater than d. The total time required tau k to execute all instructions is tau k equal to k plus n minus 1 into tau. The speed up factor for the instruction pipeline is compared to the execution without the pipeline is defined as sk equal to t1 by tk equal to numerator part nk tau, denominator part k plus n minus 1 into full into tau, that equal numerator part nk by denominator part k plus n minus 1, numerator part nk by k minus 1 plus n. If the number of instructions executed is much higher than the number of stages in the pipeline, then sk equal to k. Pipeline hazards. Any condition that causes the pipeline to stall is called a hazard. Mainly, there are three types of hazards: structural hazards, data hazards, control hazards. Pipeline performance analysis. Cycles per instructions of a pipeline processor. Suppose an n-segment pipelining processor emits instructions without stalls or penalties. We know that it takes n-1 cycles to load, set up the pipelines, and m cycles to complete the instructions. The number of cycles n cycle equal to capital N plus capital M minus 1. The cycles per instruction CPI equal to n cycle per m equal to 1 plus n minus 1 whole by m. 1 separate to n minus 1 numerator part to m denominator part. Effect of stalls on CPI. Suppose that we have n segment pipelining processing m instructions and we must insert k stalls to resolve data dependencies. The pipeline has set up penalty of n minus 1 cycles as before, a stall penalty of k cycles, and a processing cost as before of m cycles to process the m instructions. The number of cycles n cycle equal to capital N plus capital M plus k minus 1. The cycles per instruction CPI equal to n cycle per m, that equal to 1 plus of numerator part 1 and separate plus numerator part n plus k minus 1 by m. M is the denominator part. Arithmetic pipeline. An arithmetic pipeline is similar to assembly line in a factory. Data enters a stage of pipeline which performs some arithmetic operations on data. The results are then passed to the next stage which perform its operations, and so until the final computation has been performed. The speed up of a pipeline processing over a equivalent non-pipeline processing defined by the ratio S equal to NTN. NTN is the numerator part. K plus by denominator part k plus n minus 1. Adanto bracket lo pedtam k plus n minus 1 into TP. NTN by k plus n minus 1 into TP. As the number of tasks increases, n becomes much larger than k minus 1 and k plus n minus 1 approaches the value of n. Under this condition, the speed up becomes S equal to Tn by Tp. If we assume that the time it takes to process a task is the same in the pipeline and non-pipeline circuits, we will have Tn equal k Tp. Including this assumption, the speed up reduces to S equal to k Tp by Tp equal to k. This shows that the theoretical maximum speed up that a pipeline can provide is k, where k is the number of segments in the pipeline. Sum of two continuous time periodic signals may or may not be periodic. Ideal CPI pipeline equal to 1. CPI pipeline equal to ideal CPI pipeline plus pipeline stall cycles per instructions. 1 plus pipeline stall cycles per instruction. Speed up equal to average instructions time unpipelined by average instructions time pipelined. CPI unpipelined by CPI pipelined into clock cycle unpipelined by clock cycle pipelined. ఈ రెండు సెపరేట్. CPI clock cycle రెండు సెపరేట్ అనమాట. ఓకేనా, డోంట్ కన్ఫ్యూజ్. That equal to numerator part CPI unpipelined into clock cycle unpipelined by denominator part 1 plus pipeline stall cycles per unit into clock cycle pipeline. That equal to pipeline depth numerator part of the denominator part 1 plus pipeline stall cycles per instruction. Computation of speed up with branch penalty. Pipeline speed up equal to numerator part pipeline depth denominator part 1 plus pipeline stall CPI. That equal to numerator part pipeline depth by 1 plus denominator part 1 plus 1 separate branch frequency into branch penalty. If A is n times faster than B, n equal to execution time B by execution time A. That equal to 1 by performance of B by 1 by performance of A. That equal to performance of A by performance of B. If A is n% faster than B, n equal to performance of A minus performance of B whole by execution of B into 100. That equal to execution of time B minus execution of time A. That is the numerator part whole by execution of time A. That execution of time A is the denominator into 100. VLSI testing. After the fabrication of the integrated circuit IC, it must be verified. VLSI testing means checking of the manufacturing IC to verify its correctness. If test results are satisfactory, then only the chip is qualified to the ship to the customer. Importance of testing. The product quality is measured in terms of defects. More the number of defects chips, poorer will be the quality of the chips. Another important aspect of testing is the testing time. Let us consider a combination circuit having n inputs. To test this circuit completely, we need 2 power n number of possible input combinations or test vectors. In case of sequence circuits, the required test vectors would be 2 power n plus m. Power lo undedi n plus m 2. If there are m number of registers, test during the VLSI life cycle. Testing typically consists of applying a set of test stimuli to the inputs of the circuit under test while analyzing the output responses. Circuits that produce the correct output responses for all input stimuli pass the test and are considered to be the fault free. Input test stimuli, input 1 and so on, input n, circuit under test CUT, దాని యొక్క అవుట్పుట్ ఏమో అవుట్పుట్ రెస్పాన్స్ అయిన సిస్టమ్ దానికి పాస్ ఆర్ ఫెయిల్ ఇస్తాం. A testable circuit is defined as a circuit whose internal nodes of interest can be set 0 or 1, in which any language change into the desired logic value at the node of interest due to fault can be observed externally. Challenges in VLSI testing. The physical implementation of VLSI design is very complicated. Any small piece of dust or abnormality of geometrical shape can result in a defect. Defects are caused by processing variations or random localized manufacturing imperfections. As the integration scale increases, more transistors can be fabricated on a single chip, thus reducing the cost per transistor. However, the difficulty of testing each transistor increases due to the increased complexity of the VLSI device and increases potential for defects, as well as the difficulty of detecting the faults produced by those defects. Test principles. A fault is a representation of defects reflecting a physical condition that causes a circuit to fail to perform in a required manner. A failure is a deviation in the performance of a circuit or system from its specified behavior and represents an irreversible state of component such that it must be repaired in order for it to provide it to its intended design function. Exhaustive testing. If the CUT is in an W input combination logic circuit, we can apply all 2 power n possible input patterns for testing stuck at faults. This approach is called as exhaustive testing. Functional testing. In this testing, every entity in the truth table for the combination logic circuit is tested to determine whether it produces the correct response. Structural testing. The approach of structural testing is to select specific test patterns based on circuit structural information and a set of fault models. Structural testing saves times and improves testing efficiency as the number of test patterns is decreased because the test vectors target specific faults that would result from defects in the manufactured circuit. Fault coverage. Fault coverage equal to number of detected faults by total number of faults. fault detection efficiency equal to number of detected faults by total number of faults, number of undetected faults. Total number of faults, number of undetected faults, fault coverage is linked to the yield and defect level by the following expression: defect level equal to 1 minus yield whole power 1 minus fault coverage, 1 minus separate 1 minus fault coverage in under brackets yield power 1 minus fault coverage. Finally I will read 1 minus yield power 1 minus fault coverage. Fault simulation. Any input pattern or sequence of input patterns. Fault simulation. Any input pattern or sequence of input patterns that produces a different output response in a faulty circuit from the fault-free circuit is a test vector or sequence of test vectors that will detect the faults. The goal of test generation is to find an efficient set of test vectors that detects all fault concentrations for the circuit. Design for testability. DFT technique generally falls into one of the following three categories: ad hoc DFT techniques, level sensitive scan bridge design, LSST design or scan design, built-in test, self-test, BAST. Ad hoc DFT techniques. Ad hoc testing combines a collection of tricks and techniques that can be used to increase the observability and controllability of a design and that are generally applied in an application-dependent fashion. Scan test. The automatic test generation methodology is well suited for combination circuits but at very useful for sequential circuits. Therefore, for the sequential circuits, a different technique is used which is known as scan design. In this process, all the flip-flops are replaced by a scan flip-flop SFF. The SFF has two modes of operation: normal mode, in which flip-flop is operated in the conventional mode, and scan mode, in which the flip-flop operates are connected serially to form a large chain of shift registers throughout the entire chip. Serial scan test. In the scan mode, the scan in data input flows through the chain of registers as illustrated by the dotted line. In the normal mode, the normal input flows through the registers and the combination logic blocks as shown by the solid lines. Now, register combination logic register output, scan in, scan out. Parallel scan test. For large circuits, the size of the scan chain is too big and the scan test requires a significant amount of time to avoid this. The whole scan chain is divided into small scan blocks and each block is scanned individually. This greatly saves the overall scan test time. Boundary scan test. Boundary scan test is an integrated method for testing interconnects on printed circuit boards PCBs that are implemented at the integrated circuit IC level. The boundary scan test architecture provides a means to test interconnects between integrated circuits on a board without using physical test probes. It adds a boundary scan cell that includes a multiplexer and latches to each pin on the device. Cells on device primary inputs are referred to as input cells. Cells on primary outputs are referred to as output cells. Input and output is related to the internal logic of the device. Built-in self-test BIST. In built-in self-test, a test logic circuit is incorporated in the chip. The extra circuit generates test patterns, applies them to the input and tests the circuit. The extra circuit increases the chip size but reduces the test cycle time. The components of the BIST module are pseudo random sequence generator, PRSG, and B signature analyzer. Design economics. The total cost of the product is separated into two components: fixed costs, variable costs. Fixed costs are independent of the number of chips sold. The variable cost includes the cost of assembly, cost of manufacturing, and the cost of parts used into the product. We can write the total cost as total cost equal to fixed cost plus brackets fixed cost separate plus variable cost into volume of chips. Variable of cost into volume of chips రెండు మాత్రం బ్రాకెట్స్లో ఉంటాయి. Yield and reject rate. Yield is a process determines the profitability of semiconductor company. Yield is defined as the ratio of number of good chips to the total number of fabricated chips on a wafer. Yield can be written as yield equal number of good chips by total number of fabricated chips. The random defects are characterized by two factors: the defect density D and B, the clustering parameter alpha. The average number of defects on a chip area is A into D. Yield can be expressed as Y equal to 1 plus 1 separate numerator AD by alpha separate 1 plus AD by alpha whole power 1 minus alpha whole power 1 plus AD by alpha whole power minus alpha. For an unclustered model, above equation reduces to Y equal to E power minus AD. There are two types of yields loss: catastrophic and parametric. Catastrophic yield loss is due to random defects and parametric yield loss is due to process variations. Automation of and improvements in a VLSI fabrication process line drastically reduce the particle density that creates random defects over time. Parametric variations due to process fluctuations becomes the dominant reasons for yield loss. When ICs are tested, the following two undesirable situations may occur. A faulty device appears to be a good part passing the test, a good device fails the test and appears as faulty. These two outcomes are often due to a poorly designed test or the lack of design for testability. Result of the first case, even if all product pass acceptance test, some fault devices will still be found in the manufactured electronic system. When these faulty devices are returned to the IC manufacturers, they undergo FMEA for possible improvements to the VLSI development and manufacturing processes. The ratio of field rejected parts to all parts passing quality assurance testing is referred to as the reject rate, also called as the defect level. Reject rate equal to number of faulty parts passing final test by total number of parts passing final test.